So, hello, my name is Elverton and I will present our final project in this subject. So, before I start, I want to emphasize that this presentation is an overview of our work. To get a deeper explanation, please read our final report. So, let's start. First of all, I want to give some motivation about this work. We had a previous work where we did about graphs called span bands. In this work of span bands, we found a potential to analyze clusters temporally. And also, cursing this subject, we read a paper from KDD which evaluates graphs temporally. So we have a topic to explore for the final project. But what is a span band after all? Well, a span band is a group of machines correlated by the message they send. Probably these machines belong to the same spammer. In the picture in the slide, you can view the process to create the graph of a collaboration. We have the machines as nodes and the edges if two IPs participate of the same campaign. For example, in the picture we have the IP final 22 having messages in campaign 1 where IP final 23 have either. So they have an edge between them. Given the graph, we apply a technique we proposed in the previous work to detect the communities or span bands. Here we have a picture of a span band, and our objective from now on is to analyze these groups over time. In the beginning of the project, we realized that the campaigns could be improved by using a more representative label for the URLs, which are one of the features used to group messages. So why we want to improve these campaigns? Well, because improving the campaigns, we improve the span bands either. So in the picture in the slide, you can see that many URLs can point to a same destination, like YYY, and AAA points to URL1. I will not spend much time explaining it because it is well described in the final report. We spent more than a month studying it, and the conclusion is that we can use the IP that answer for a URL as its representation. Here you have an overview of the possible representations of a URL. The IPs that we use is the initial and final IPs, and we explain it in the final report, as I said. So now, here we get in the paper from KDD, written by Azure et al. It is an amazing paper in my opinion. I will say Azure instead of Azure at all in order to avoid say at all many times. So the paper proposes techniques in order to evaluate graphs snapshots over time. The granularity of the evaluation is cluster and vertex. Like here we have clusters. For cluster, Azure proposed 5 metrics, as you can see in the 5 pictures. Continue, split, merge, form, and dissolve. We explain short them in our report. In this slide I bring some examples of the metrics to show that they are very intuitive. For vertex, Azure proposed 4 metrics: leave, join, disappear, and appear. They are very intuitive either, and it is explained in the report, and of course in the original paper. Based on the metrics, Azure proposed 4 index. We use 3 in our work, and it is described in the slide. Briefly, we have the stability index that measures the tendency of a node to have interactions with the same nodes, sociability index, which measures the measure of the number of different interactions that a node participates in, and influence index, which is a measure of the influence of a node has on others. It's important to mention that we implement all the metrics and the index, and this cost us some time to get everything work fine. Okay, here we have an overview of the data set. As can be noticed, we have a lot of data, and we want to discover patterns that can help us to answer some questions like, well, what IP address that should have more attention? What happens with the spam band along the days? Well, these questions we want to answer now. So here we present the most in this remaining of slides, we present the most important results, because there is a lot of results in the final report, but here we mention the important ones. Well, here we use the raw metric of leaves and joins. The results, as you can see, show that it varies depending on the honeypot. As you can see in the picture, the honeypot BR01 has more leave and join events than EC01. And the conclusion is that this indicates the spam bands from those honeypots communicate more among them. In honeypots like EC01, the number of leave and joins are really small, okay, and probably because its spam bands are more independent from each other, and there isn't a lot of communication among their IPs. And only to comment, this is a new result for us and show two types of behavior in honeypots. One with IP address interacting and others with a lack of this interaction. Okay, and here we have the results using the stability index. I will show you only one honeypot, but the final report, as I said, has the results for all of them. Many honeypots had a particular behavior. A small number of IP addresses have stability index equals 0, and 20% of them have stability index greater than 1000, like you can see in the honeypot AU01. And well, this conclusion shows us that we have a lot of spam bands that are stable over time, have IPs that are stable over time, and this is a very new result for us and deserves more attention in future works. Okay, and now we show the results using the sociability index. Again, we show for only one honeypot, but the final report have all of them. Well, IP addresses. We observed that IP address in many honeypots had sociability index 0 or close to 0, and just a few of them have high values of sociability index. As you can see in the figure in the slide, the honeypot BR01 has some of its IPs interact among themselves, while BR02 do not. Correlating with analysis we did using influence index that we show in the final report, and we will not show here, we found some IPs in BR01 and in other honeypots that have a behavior similar to BR01 that are sociable and influenced together. So thus this is interesting study that we can have in a future work in order to understand better the contribution of these IPs in the span dissemination. And finally, we analyzed more deeply the IP address with higher sociability index. This that we mentioned, that I mentioned now, and we found that of the 10 IP addresses with the highest sociability index belong to the same autonomous systems, 4.1, 3.4, like as you can see in the slide. This result shows that we can combine this work with another previous work of ours called Neighborhoods and Condominiums, which classify neighborhoods of autonomous systems. So thanks for watching, and for more details please read the final report.